How do we perform our network analysis? How does the computer perform the network analysis? The more importantly, we can start with a basic algorithm, Dijkstra's algorithm here. This introduces the first concepts, and we will develop this a little bit further. But we'll get to get through the basics of this. It's going to take a little while, but we'll get there. The details are of interest to understand the problems that can arise, and some of the difficulties we have in our analysis, and why network analysis doesn't always give us the perfect answer. But remember, the computer will be doing this for you. So we're going to examine this, this algorithm using the concept of a stack of cards. This is actually not dissimilar to how the computer would be working, an efficiently programmed computer algorithm for solving this. We have a stack of cards where each card, each one of these long things here is a card, and each one represents a node in our network. So the middle square on each card is the name of the node. The left tells us what was the previously visited node. Because we're doing a network analysis, we're going to be going from node to node to node. What was the previous visited node? And alpha is our starting node here. We're going to go all the way to omega down here. That's where we want to get, from alpha to omega. And the cost of getting to alpha, well, we've started there, so it's cost us nothing. Our initial cost is 0, that's where we start from. And we want to get to alpha, and we will incur a cost, and we want that to be as small as possible. Whether that's travel time or whatever it is, just plain distance, something, whatever these numbers represent along our network. And if we look here carefully, we can see that from alpha, we can access A, B, and C. So we have these 3 cards labeled up here, A, B, and C, and they can all be accessed from alpha. So the from node here for each of these is alpha. And the cost of getting to A from alpha is 4. The cost of getting to B from alpha is 1. Now, as we can see, this is obviously some sort of weighted cost because these distances are very similar, yet that costs 4 times as much. Whereas this very long line actually costs only 3. So that's the cost of traveling along the network from alpha to these 3 points. We can see the cards down here for the other nodes in the network, and we don't know how to access them yet, so they're blank in the left-hand square. The right-hand square is set to infinity because we want to order these cards. We're going to put them in a numerical order. The least cost rises to the top, the highest cost is below. So if we set this to infinity, they're unexamined, we don't know how much it's going to cost, we want them at the end, at the bottom of the stack, so we just set the cost to a lot. In an infinite cost. And as we can see here, A falls to the bottom place in our active stack here because it costs the most. Then comes C because that costs 3, which is less than 4. I hope you can work that one out. And then the cost of getting to B is 1. So that's at the top of our stack. That will be our next card to examine. So now we've done this, we're done with alpha. We've examined all the possibilities we've got with alpha. So let's just move that out of the way and then bring the top card up to be examined, and that's the B card. And from B, we can see A and we can see F. So let's bring up F and then examine F, and F costs us 4 to get to. That's 1 plus 3 is 4. Interestingly, when we look at A, that has been changed to 3 now. It no longer costs us 4 to get to A. We travel via B. We change this from alpha to B because we're going to B first, and then we're going to A. And that will cost us only 3. We actually managed to reduce our costs down to 3 by, instead of going along this very expensive route, go via B. So that's a perfectly valid analysis. And the cost, again, of traveling down to F is going to be 4 in total via B. So to get to F, we have to come from B in our analysis so far, and it will cost us 4. That's how the computer is going to be doing this. And we continue our analysis. We reorder everything, so they've been reordered, and And we can see here that C was already in the stack, so that's prioritized, that's at the top, because these both cost the same. So we move that card out of the way, continue our analysis over to C. Well, so we wanted to be going down there, and now we're going over there. Okay, that doesn't feel optimal. And we've started to see some of the potential problems here, but we don't know. This could be right. This could be a quick path through. So let's just see. And from C we can see G. So we pulled up the G card there, and we'll give that a value. That's 5. That's 3 plus 2 gives us 5 to get to G. And to get to G we have to come from C to get that cost as well. So that was the last one visited before we could get to G. We're not actually standing on G yet. If we go from C, we can get to G for a cost of 5. And everything else is unchanged. Okay, so reorder the stack. The next one is going to be A. So now we move that up there, move that over there. You can see now we're standing at A, and at A we can see E. And we can see B as well, but well, that's already been dealt with, so we don't need to worry about that. So E, yeah, let's just add the cost of that there. We can access E from A, and it will cost us 5. 1 plus 2 plus 2 is 5. Good. And the last point of access, the last node that we visited to get to E will be A. Oh, we're getting down there soon. So let's carry on our analysis. And now we move to F. Now what do we see from F? F, we can see omega. It feels like we're getting somewhere now. So now we can see the goal. That's where we want to be. So let's just calculate. That's going to cost us 7 to get to omega via F. Oh, I think, are we done? No, we're not done. We're not done because there could, in theory, be a route, a path from G directly to omega that only costs 1. And that would be a cheaper path, because at the moment to get to G it costs us 5. 5 plus 1 would be 6, which is less than 7. So we need to investigate. Is there actually a cheaper path? Is there? Well, we can see that there isn't, but the computer doesn't see that yet. So the computer needs to investigate. So we have to go to G. We look at G and we say, well, what is there? We can see D and I, and we add those in and analyze the costs. It costs us 7 to get to D. We go via G, and it costs us 6 to get to I. Reorder that and move up. Well, the next one is E, because that's got a value of 5. There might be a path over from E to omega directly, so that would be cost us 6. And so on and so forth. We move through the network, having to do this analysis every time, until finally, yes, we're there. There is no shorter path. We've found our way through to omega. But what was that path? Well, to find out what the path is, we look at the stack of cards. So we take down the F there, because that's the one we needed. We accessed omega by coming from F. Okay, so how did we get to F? Well, we went from B. Well, that's not B. That's not B. There's B. So we take down B, and we say, okay, so how do we access B? We access B from alpha. Where's alpha? That's that card there. There's our route. We go from alpha to B to F to the route that we could see ourselves with our brilliant brains. We actually managed to work that out far out of the computer. The computer needed to do a lot more work to get there, but it got there in the end. It found that shortest route. And that's how the simple Dijkstra algorithm works in essence.